everyone. Today we are going to learn synthesis of polymeric nanoparticle. In today's lecture, we will be learning about polymeric nanoparticle and its properties, and we will also learn how to synthesize and characterize albumin nanoparticles both theoretically as well as practically through demonstration. Let us see what is polymeric nanoparticles. Polymeric nanoparticles are solid particles in colloidal form, and these polymeric nanoparticles are mainly composed of biocompatible and biodegradable polymers. Biocompatible means the particular polymer should be compatible to the biological system, and biodegradable means if the particular polymer degrade inside the body, it should not induce any adverse effects, that is biodegradable polymer. Mainly these polymeric nanoparticles are useful for drug delivery application. We can load the therapeutic drugs into this polymeric nanocarrier and we can target these nanocarriers to specific location. For examples, so the drug can be loaded inside the polymeric nanocarrier, that is called drug encapsulation. And we can also add the drug on the surface through physical process like adsorption. So, the drug can be attached on the surface, and third one is the drug can also be entrapped into the polymeric network, that is called drug entrapment. So, we have to select the right polymers because selecting the right polymers will affect your biodegradability, biocompatibility, and also based on your polymer, it will improve the therapeutic efficacy and it will lower the side effects. These polymeric nanoparticles can be categorized based on the methods of synthesis. For example, from preformed polymers in dispersion, we can use a method such as solvent evaporation or nanoprecipitation, emulsification, dialysis and supercritical fluid technology for making that nanoparticle from the preformed polymers. From monomers, we can make polymeric nanoparticles by emulsification, mini emulsion and other techniques like radical polymerization and interfacial polymerization. From hydrophilic polymers, we can make the polymeric nanoparticles by ionic gelation or co-adsorption. So, based on the polymers, we have to select the suitable method for synthesis. We can select any of the methods, depends on the polymer and depends on your final application. Let us see the types of polymers used to synthesize polymeric nanoparticle. The first one is natural hydrophilic polymers. We can use the natural proteins like gelatin or albumin or natural polysaccharides like alginate and chitosan. The other one is synthetic hydrophobic polymers. It can be preformed polymers like polystyrene and polycaprolactam, that is PCl, or it can be polymerized during the process such as polymethyl methacrylate. The third one is amphiphilic block copolymers, which contains polymers with both hydrophobic as well as hydrophilic group in the polymeric molecule, and some of the examples are like diblock, triblock and tetrablock copolymers. Let us see some of the examples of biodegradable polymers and its application. The first one is polyester. Under polyester, we have polylactic acid. Under proteins, we have silk fibroin and albumin. In today's lecture also, we are going to learn how to synthesize albumin nanoparticles, and under polysaccharide, we have examples like starch, cellulose, and under polyphenols, we have lignin and tannin. Under lipids, we have waxes and surfactants. These biodegradable polymers have wide application including food packaging, drug delivery, tissue engineering and including sensors. Let us learn about protein based nanoparticles. Protein based nanoparticles have emerged as a potential candidate for various therapeutic as well as diagnostic application because it has a high biocompatibility and high water solubility, and also it is easy to modify the surface of this protein nanocarriers. So, that is one of the important property. Abraxane, this is the first FDA approved albumin based drug nano formulation. So, based on the success of this Abraxane, these albumin based nanoparticles have gained overwhelming response, and lot of research group is working on in developing these protein based nanoparticle for various application including cancer therapy. The another important property of this protein based nanoparticle is the presence of functionally charged groups including amino and carboxylic groups, and that will be very helpful for adding the functional groups and targeting these nanocarriers to specifically to the cancer. As I told you earlier, these protein based nanoparticles have wide applications in drug delivery because of its biodegradable nature and easy to modify the surface, and also it is easy to synthesize and it is a cost effective and it can hold hydrophobic molecules. As you know, the most of your anti-cancer drugs are hydrophobic in nature. We can load the hydrophobic drugs into these protein-based nanocarriers. And it also have enhanced circulation time. That means it can stay in your body for more amount of time, and it can release that drug in a slow and controlled way. And also it has a preferential cellular uptake. For example, these protein nanoparticles are taken up more by the cancer cells, and there is no toxicity. So these are the advantages of these protein-based nanoparticles for drug delivery applications. As I told you earlier, this Abraxane is the first albumin-based nanoparticle approved by FDA. Based on the success of this Abraxane, there are several albumin-based drugs and imaging agents in the market, and some are under clinical trials. Let us see what is Abraxane and how Abraxane was made by nanoparticle albumin-bound technology. Abraxane is solvent-free nano version of Taxol, and it was approved by FDA in 2005 for breast cancer therapy. You can see the difference between the Taxol and Abraxane. In the Taxol, we have only 6 milligram of paclitaxel, that is the anti-cancer drug. And to dissolve this 6 milligram, we have to use chromophore and ethanol. In case of Abraxane, we have 100 milligram of paclitaxel in 900 mg of albumin. There is no use of surfactants or solvents in the preparation of this albumin-based nanoparticle. That is the advantage of this Abraxane. It has more therapeutic effect when compared to the Taxol, which has only less concentration of your anti-cancer drug. Based on the success of Abraxane, various research groups developed tumor-targeted delivery of anti-cancer agents and imaging agents. For example, we can target the drug and imaging agent specifically to the breast cancer by conjugating the albumin nanoparticle with folic acid. If a nanoparticle is conjugated with folic acid and the breast cancer have the receptor for the folic acid, so this nanoparticle will go and specifically bind to the breast cancer cells, and it will not bind to the normal cell. In this way, we can improve the therapeutic efficiency by specifically targeting to the tumor cells. And we can also add gold nanoparticles or gold based nanostructures to this, and we can use it for photothermal therapy. Photothermal therapy means we can apply the light and that will generate the heat and it can destroy the cells. And we can also use iron oxide based nanoparticles. When you are using this iron oxide nanoparticle with the help of magnetic field, and we can increase the temperature in the particular location, that is called hyperthermia. By that way also we can kill the cancer cell. Let us see how to synthesize bovine serum albumin nanoparticles. We can prepare BSN nanoparticles by desolvation method. By desolvation method, we can achieve homogeneous distribution and less aggregated nanoparticles. In this method, we will be using ethanol as desolvating agent and glutaraldehyde as cross-linking agent. And nanoparticles prepared by this method shows great stability in water as well as cell culture medium. Let us see how this glutaraldehyde is used as a cross-linking agent. This glutaraldehyde will form a skip base on reaction with protein. The positively charged amino groups of the protein react with the 2 carbonyl groups present in the glutaraldehyde. By this way, it will cross-link and make the stable protein-based nanoparticle. Let us see the overview of BSN nanoparticle synthesis by desolvation method. Once you prepare the aqueous solution of albumin, we have to add the desolvating agent, that is ethanol. Once you add ethanol dropwise, it will gradually reduce the albumin solubility and that leads to phase separation. And in this step, if you want to add any anti-cancer drug, we can also add the anti-cancer drug. As I told you earlier, most of the anti-cancer drugs are hydrophobic in nature. We can dissolve the anti-cancer drug in this ethanol or acetone, and we can also add dropwise. Then the drug will be encapsulated into the nanoparticle. The albumin aggregates or nanoparticle formed at this stage are unstable. It may dissolve back into solution. To avoid that, we have to add cross-linking agent, that is glutaraldehyde. After the cross-linking step is over, we have to do centrifugation to remove the unreacted cross-linking agent. After the centrifugation, discard the supernatant and add deionized water and repeat this centrifugation step for at least 3 times to completely remove the unreacted cross-linking agent. Then you can lyophilize and add the powder with deionized water to make the desired concentration of your protein nanoparticle. By this way, we can make the stable albumin nanoparticle. In today's lecture also, we are going to learn how to synthesize this BSA nanoparticle by this method more in detail through practical demonstration. Let us see the mechanism behind the cellular uptake of BSA nanoparticles. Albumin is a key protein in cancer progression by supplying nutrients for tumor growth. That means the tumor cells need more amount of nutrients, and this albumin protein is required for its tumor growth. And once you are adding the anti-cancer drug to the albumin, the cells take up this albumin nanoparticle, assuming that this is the food for its growth. But however, this albumin nanoparticle is having the anti-cancer drug, so it can enter into the cell and it can kill the cancer cell. How this albumin is entering into the cell? It is entering through GP60 receptor, that is glycoprotein receptors present on the surface of the cells, and it leads to cavulae formation. Cavulae formation, it provides the entry in the cell and it allows the nanoparticle to enter into the cell. Once it crosses the barrier, it enter into the cell and release the anti-cancer drug and it induces the cell death. And these BSA nanoparticles interact with the secreted protein acidic and rich in cysteine, that is spark protein, to get into the tumor cells, and these tumor cells overexpress the spark protein. So, these BSA nanoparticles can easily go and attach to the cancer cell which overexpress this spark protein. By this way, we can target the nanoparticles to specifically to the tumor cells and we can kill the cancer cells. Let us see how this nanotechnology is improving the cancer therapy. In case of traditional treatment, when you are using these anti-cancer drugs, it cannot distinguish the cancer cells and non-cancerous cells. It will go and attack all the cells. At the end, all the cells will die. That leads to a lot of toxic and side effects. In case of nanotechnology, what happens is these nanoparticles are specifically targeted to the cancer cells. It will kill only the cancer cells and the non-cancerous cells are intact. So, that is the advantage of this nanoparticle based tumor targeted delivery. There are two approaches to target the nanoparticle to the cancer cell. One is passive targeting, the other one is active targeting. Let us see what is passive targeting. This passive targeting is based on the retention effect of particle of certain hydrodynamic size in cancerous tissue. For example, if you are making a nanoparticle of size between 70 to 200 nanometer, these nanoparticles will be trapped in the tumor location by an effect called EPR effect, enhanced permeability and retention effect. So, this I will explain later. And the next approach is active targeting. Here we have to add specific functional group or we have to add antibody specifically for the cancer cell. Once you add the antibody specific for the cancer cells, these nanoparticles will go and bind specifically to the cancer cell and destroy the cancer cell. This is called active targeting. Let us see what is EPR effect. Tumors need blood to grow larger than 2 mm in size. What happens is these tumorous tissues suffer of enhanced permeability and retention effect, that is called EPR effect, and these nanoparticles injected in the bloodstream do not permeate through the healthy tissues and this will be trapped in the tumor region. This green color is the tumor region, where you can see that there are a lot of leaky blood vessels. Due to that, if you are making a nanoparticle between 70 to 200 nanometer polymeric nanoparticles, so this will be trapped in this tumor location and that will kill the tumor cells. Let us see what is active targeting. So, in the case of active targeting, as I told earlier, we have to add specific ligand, we have to add antibody or we have to add the particular protein or peptide, and that will specifically bind to the cancer cell, and once it bind to the cancer cell, then it will kill the cancer cell. Whereas, in case of normal cell, we don't have that kind of receptors, so this nanoparticle cannot bind to the normal cell. It specifically bind only to the cancer cell and it will kill the cancer cell. In addition to the anti-cancer drug, we can also add the imaging agent. In that case, we can call this nanoparticle as a theranostic nanoparticle, which can be useful for both therapy as well as diagnostic. Let us see how to characterize these BSA nanoparticles. We can characterize the BSA nanoparticles using UV visible spectrophotometer. In this UV visible spectra, you can see there are two peaks for the niclosamide drug alone, one at 260 nanometer and one at 346 nanometer. And once this niclosamide drug is encapsulated into the BSA nanoparticles, and you can see the peak at 346 nanometer for the drug loaded BSA nanoparticle. The slight change in the spectra, it is due to the cross linking between the amino acids of protein and the formation of protein drug nanoparticle complex. And from this picture, we can understand the insolubility of niclosamide in water and solubility of BSA niclosamide nanoparticles in water. When you see the niclosamide drug under the scanning electron microscope, you get this kind of structure. And same thing, once the drug is loaded into the protein nanoparticle, you can see here the spherical shape nanoparticle which is loaded with the niclosamide. And the nanoparticles can also be observed under the AFM, that is atomic force microscope. You can see that the protein nanoparticles are spherical in nature, and by using this dynamic light scattering DLS, you can also get the hydrodynamic size. The hydrodynamic size is also in the range of roughly 200 nanometer. By using this electron microscope and atomic force microscope and by DLS, that is the dynamic light scattering, we can understand the size as well as the shape of your protein nanoparticle. We can study the anti-cancer efficiency of niclosamide loaded BSA nanoparticles compared to niclosamide by using cell viability assay. In cell viability assay, if we see that when you add niclosamide, which is a hydrophobic drug, it is not able to enter into the cell, it is not able to kill the cell. The cell viability is close to 100. But when you load this niclosamide drug into the protein nanoparticle, you can see that the number of cells percentage is going down with respect to the concentration. By using this cell viability, we can also calculate the IC50. IC50 means the concentration required to inhibit 50% of the cell growth. In this case, we are using A549, that is a lung cancer cell line, and you can see that the IC50, the 50% is 5 micromolar. You can use the 5 micromolar to kill 50% of the lung cancer cells. In case of breast cancer cells, you can see that the IC50 is roughly around 2.6 micromolar. The IC50 concentration will vary from cell to cell. So, that is why we have to use several cell lines to understand the therapeutic efficiency of your nanoparticles. Let us see some of the troubleshooting tips in synthesis of BSA nanoparticles. If you are observing particle aggregation, it may be due to clumping or large aggregates in the suspension. How to overcome that? You can check the pH of the solution, add desolvating agent dropwise, or you can use the optimum concentration of polymer. And next one is, if you are observing irregular particle size, that is wide distribution of particle size or inconsistent size, how to overcome that? You can ensure consistent and vigorous stirring during solvent addition. Add the crossing agent only after achieving uniform particles. And next one is, if you are getting low yield of nanoparticles, it may be due to low recovery of nanoparticles. You can adjust the centrifugation speed and optimum polymer concentration. Check batch to batch variation of all the reagents, and if you are facing increased turbidity, that means the solution appears turbid or particles are visible without magnification, you can use 0.22 micrometer filter to remove any large aggregates. Wash the nanoparticles with distilled water to remove excess reagents. And if you are facing reproducibility challenges, that means variation in the particle size or yield across the batches, you can use consistent reagent quality, equipment and environmental condition. Always prepare fresh polymeric solution to avoid degradation effects. Hope you got the overall idea about how to synthesize BSA nanoparticles and also how to characterize the BSA nanoparticles. Let us go to the lab and learn this technique more in detail. To synthesize BSA nanoparticles, we need BSA powder, glutaraldehyde as a crosslinker, vials, magnetic bead, sterile ultra pure water, spatula, absolute ethanol, sterile syringe, tips and pipette. First we will weigh 50 mg of BSA powder using a weighing balance. Then add this BSA powder into a vial. Add 1 ml of sterile ultra pure water to it and keep it on stirring at 400 rpm. Wait till the BSA is completely dissolved in the water. After complete dissolution, we have to add 4 ml of absolute ethanol into the solution. For that, we will use a sterile syringe. Add absolute ethanol to the BSA solution drop by drop. A cloudy formation will be seen in the vial, indicating the phase separation. You can see that the solution is getting slightly cloudy. So now the solution is completely cloudy. Once the solution has turned cloudy, we will add 30 microliter 8% glutaraldehyde to the BSA solution. We have to add it very quickly and keep it on stirring overnight at 400 rpm. You can observe the color change in the solution, which denotes the successful synthesis of BSA nanoparticles. Moving on to the washing step, we will take out the magnetic beads from the solution and pour the solution in a centrifuge tube. Similarly, prepare another tube with equal weight to balance the centrifuge tube with sample. We have to do centrifugation of the solution for about 30 minutes at 8000 rpm. To balance the centrifuge, you should place the tubes of equal weight directly opposite each other in the rotor. Start the machine and wait for the centrifugation to be completed. After centrifugation, carefully remove the centrifuge tube. You can see that there is a pellet formation at the bottom which contains BSA nanoparticles. We can discard or store the supernatant in a separate tube. Add sterile ultra pure water to the pellet for washing. And again centrifuge the BSA nanoparticles at 8000 rpm for 30 minutes. Carefully take out the tube. We will discard the supernatant. This is the washed nanoparticle pellet. After this, we will proceed to lyophilization step. First, we have to turn on the compressor and wait till the temperature reaches -80 degrees Celsius. Remove the cover and place the centrifuge tube without the lid in the machine. Turn on the vacuum pump for lyophilization. After lyophilization, carefully release the pressure and take out the tube. So now we weighed 30 mg of lyophilized BSA powder. Now we will add 1 ml of sterile ultra pure water into the tube to get a final concentration of 30 mg per ml. So here we have made a stock solution of BSA nanoparticles. As a summary, in today's lecture we learnt about what is polymeric nanoparticles and also how to synthesize and characterize BSA nanoparticles. We also learned the applications of BSA nanoparticles in drug delivery. Through practical demonstration, we also learned how to synthesize and characterize BSA nanoparticles. Thank you for your kind attention. I will see you in another interesting lecture.